Good evening, nerds. Oh, yeah, I should probably... God, I wish I had 3 arms. Okay. Laser. Got it. So what I lack in wit, I make up for in costuming. So if I start rambling, please just look at the tiara. That's why it's here. And wait for the next pretty picture. Tonight, I'm going to be talking to you about some research I did when I was an undergrad, where we found a subsurface ice deposit on Mars that no one had seen before. I did this when I was at the University of Western Ontario, but it was in collaboration with the University of Texas, so it's got that logo connection for y'all. And I call it the worst utopia ever because the area I'm studying here is called Utopia Planitia. It's like a Latin Martian geography joke, so now you know. Okay, so since this is ostensibly a talk about astronomy and not rocks, I thought I would include an image from Hubble of Mars at its most recent opposition. Does anyone here know what opposition is? Astronomy nerds in the audience, just shout it. Yes, exactly. And actually, the rest of this talk is about that kind of opposition and not astronomy. Any other ideas? It's actually kind of given away in this diagram right here. Yeah, okay, perfect. Someone said it. So opposition is when you have Earth in the middle, the sun on one side, and Mars is opposite the direction of the sun relative to Earth. And it tends to be when Mars is the closest to Earth when we get the nicest pictures, like this one from Hubble. That concludes the astronomy portion of this talk. So let's all pretend we're planetary scientists, like me. Does anyone have any observations from this Hubble image, this beautiful Hubble image of Mars? Is there anything remarkable about it?
It's red.
It's red, that's right. We see a lot of this orangey stuff throughout most of the planet. Does anyone see anything else?
It almost seems like one of the poles is off to the right side.
Yeah, what's up with this really bright white thing here?
The icy region?
There are icy regions here. This isn't one of them. But that was a really good observation. Does anyone have any ideas what this might be? Clouds, yes, that's right. Those are clouds. We see clouds all over the place. Look at this. Look at all these atmospheric processes. And the last observation, which was kind of already made, except in the wrong place. Does anyone see anything else worth mentioning?
It's not all red.
It's not all red. I mean, that's kind of cool. I'm not going to get too much into that, but that's just differential dust coverage. Really, all of Mars kind of looks like this dark stuff, but there's more dust in the orangey parts. The last observation I wanted you to make was that we have these white spots at the north and south poles. They're kind of obscured by clouds, but those are actually water ice. There is so much water ice on Mars that we can see it from Earth. It's on the surface. It's huge. There's a gigantic amount of it. And I've labeled it here for y'all. And also some craters. I know there's some Martian geographers in the room. I know you're here. Okay, next slide. So there's, like I said, there's a ton of ice on Mars. In the poles, most of it's captured in the poles. We have about the same amount of water ice as there is in the Greenland ice sheet. A ton of water ice. The rest of the water ice is located in what's called the mid-latitudes, so the tropics of Mars. And this ice is kind of cool. It tends to look like glaciers. There tends to be evidence of flow. And it's always buried under some rocky material. So all this gray stuff, this is all water ice, but there's some rocks on top of it. And there's enough of that to make up around 70% of the Black Sea. Okay, so now I'm going to run through over 4 billion years of Martian history really quickly. So pay very close attention. My understanding is there's a quiz later. So in the pre-Noachian, which was very creatively named relative to the Noachian period, it's mostly defined by large impact events. This is the Isidis Basin. It's around like 1,000 kilometers diameter, really big. And then we have down here, this is the Hellas Basin. This really large impact here actually marks the boundary between the pre-Noachian and the Noachian. And the Noachian, we have stuff like this happening. Does anyone know what this might be, or can anyone think what this might look like? I know I'm asking a lot in terms of audience participation. Yes, water. It looks like water. This kind of looks like, we call them valley networks, kind of looks like it might be a delta. It kind of looks like there's a lot of water flowing there. We see these kinds of features, and we associate them with the Noachian around 3.7 to 4 billion years ago. Next, we have the Hesperian. This is really big, but again, it looks like water. In the Hesperian, we have a lot of evidence of water, but it tends to be intermittent. We don't see it sitting around for a very long amount of time. This river here, this very large outflow channel looks like it formed pretty quickly. Someone's laughing. I said the Martian geographer. Okay, and then, I mean, this is all the really old stuff that happened really quickly, but most of Martian history happened in what's called the Amazonian, which is defined by ice moving around and glaciers flowing, and not a lot of liquid water on the surface. And in my very unbiased opinion, is the best geologic period of Mars. Okay, so I mentioned that we have all this ice moving around throughout the Amazonian for the past 3 billion years. This is the predominant process of stuff happening on Mars. And the reason for this is that the obliquity of Mars, the axial tilt of Mars, varies wildly. And when it's waving around, it's moving wildly. I mean, we get the movement of ice. I said that really quickly. But on Earth, okay, our axial tilt is something like 23 degrees. This is the reason why we have winter and summer. This is the reason why we have seasons. But it doesn't tend to vary much from there. It's like plus or minus 1 degree. But on Mars, the current obliquity is 25, so it's very Earth-like. The poles are cold. The equator is warm. But it can vary anywhere from 15 degrees to 45 degrees, and it may even be more dramatic than that. And what happens when you have this dramatic change in the axial tilt is you get the movement of water ice stability from the poles to the mid-latitudes or even the equator and then back again. So we have a lot of movement of water ice on the surface of Mars because of this radical variation in the axial tilt. Okay, so we know there's a ton of ice on Mars. We know it kind of moves around. It's been doing this for 3 billion years, but like, why should we care? And there's reasons that people like me care about, such that we can learn more about past Martian climate. We can learn more about the movement of volatiles on the Martian surface, and we can learn more about the interaction of ice and rock in general. So maybe the study of ice and rock on Mars can teach us something about how these materials behave on other planets, not just Earth. But then there's other reasons that most people find really sexy, like maybe there was life in the ice, or if humans go to Mars, they might want to drink the ice. And if we want to design more future missions, like we want to send more robots to Mars, maybe ice is a good target for that. And this is, gosh, so people are already having meetings, like real official NASA meetings with very smart people where they discuss where they should send humans to Mars in like the 2030s. And one of the highest priorities for these target sites when they're discussing these target sites is whether or not there's water resources there. So mapping where we can find shallow subsurface ice is really important for this like future mission, maybe human exploration thing. Okay, so narrowing in from this like very broad scale idea of how Mars works and how the ice moves around, we're going to start talking about what I did in my research. So there was a group of researchers at the university where I did my undergrad that were looking at some landforms in this area of Mars called Utopia Planitia. And they saw stuff like this here, which is kind of a depression in the ground. And like this over here, where we have this higher elevation stuff on the bottom and this lower elevation stuff up here. This is a mesa. You can see layering along the mesa if the lights were lower and the resolution were better, and sort of cracked terrain up through here. And it's really smooth. And what happens when terrestrial permafrost scientists look at these sort of features, they say, hey, it looks like there might be ice there. But we don't know if there's actually ice there right now. We don't know how much ice there might be there right now. And if there was ice involved in the formation of these features, is it still there? So there's a lot of open questions relating to this. And since we care about water ice, we want to investigate further. So I went in and I used radar to try and learn about what's happening underneath the ground around these features. I looked at a bunch of what's called Sherrod products, and I'm going to talk a bit more about those. You'll learn about those. And I looked for any radar reflectors that might be underneath the ground around these features. And if I do find these radar reflectors underneath the ground around these features, I can learn something about the electrical properties of the ground around these landforms. And knowing something about the electrical properties could be diagnostic of whether or not there's water ice and how much water ice there might be there. So a bit more about Sherrod. This is the shallow radar instrument on Mars Reconnaissance Orbiter. It's been there since 2006, and its goal is to try and map subsurface reflectors over the entire planet. And these subsurface reflectors, these dielectric interfaces, they're useful because we can learn something about the electrical properties of the subsurface. And our goal here, our golden number, is the dielectric constant, the electrical properties magical number of water ice. And we know that's 3.15. This is, if we see this, we're like, oh yeah, that's water ice, we're good. So this is how Sherrod works, okay? You have the satellite come in, it sends a radar wave towards the ground. By the way, this is the Martian surface. That orange line and that blue line is a hypothetical subsurface interface. Maybe it's ice meeting rock or ice meeting some other kind of ice. Some contrast in the composition of the subsurface that could cause radar waves to bounce back up again. Okay, so Sherrod comes in and sends the radar wave towards the ground. Some of that radar wave penetrates into the subsurface, but some of it actually reflects back to the instrument and is measured as the surface reflection. Okay, so that radar wave keeps traveling down, and if it hits a subsurface interface, if there is some kind of contrast in the composition of the subsurface, it's going to come back to the orbiter. And what happens when we do this is we get a beautiful radargram. Behold the results of our data collection. We have time on the vertical axis and distance on the horizontal axis. This, you should see when you look at this, there's kind of like two horizontal lines. There's a really bright one that's horizontal and bright, and there's a fainter one that's horizontal and much fainter. If you can't see these, you're not alone. A lot of geologists I present this to don't believe me when I tell them there's a subsurface reflector there. But I'm going to just go back and forth. That's my interpretation of where those lines are. That's what it looks like, okay? My interpretation, that's what it looks like. Raise your hand if you see it. Yes, great. I did a good job. Okay, great. So when I did this over a huge area in Utopia Planitia, I found a ton of these subsurface reflectors mapped here in purple. Here's some more examples of what those looked like. And here's sort of the distribution of them relative to elevation. They tended to occur in areas of higher elevation. So great, we have these reflectors, but why are they happening? We know we need some kind of contrast in the composition of the subsurface of this geologic material. And when I looked at the imagery, you could see here we have a bunch of smoother stuff that's kind of darker in tone. It's cracked. It's higher elevation. You see some up here and some down here. Okay, and then you have this stuff that's lighter. It's not as smooth. It's got a lot more craters. That means it's older. If something has more craters, it's had more time to accumulate them. And I hypothesized, because of the distribution of the reflectors and because of what the geology looks like, that it's this geologic contact between this older, more cratered stuff and the smoother, darker stuff that's causing these reflections. Okay? So I have my geologic interpretation. Now I need to figure out what the electrical properties of the subsurface look like so I can compare them to that of water ice to see if there's actually no water ice there. Remembering that we want this 3.15 number. Okay, so this is the only equation I'm going to show you. I think it might be the only one you've seen all night. And I'm going to, please bear with me, it's not that hard. This is just showing you velocity equals distance over time. If you've driven on the highway, you've probably done this in your head. Our velocity is the speed of light over that electrical property magical number that I introduced you to earlier. We are fortunate to know the speed of light. We know the time it takes for the radar wave to travel because of those radargram products I showed you earlier, where you all understood what was going on. And we can actually measure the distance because I've made that geologic interpretation. I can just look at the elevation of the smooth stuff and the more cratered stuff and get that parameter there. So the only thing I have left to find is the dielectric constant. Woo! Okay, so here's what those results look like. You don't really need to understand this diagram. Just know that the number that I got was 2.8, which is pretty close to 3.15. We're kind of in the ballpark. And based on this wonderful diagram, I came up with some constraints on what the composition of the subsurface might be there. So we know from my radar analysis that it's somewhere between 50 and 50% pore space, air stuff, 50 to 85% water ice, that's what we wanted, and less than 30% rock. And the total volume when I did this over the entire interface was on the order of 10 to the 4 cubic kilometers. Okay, so again, back to the interpretation. I'm secretly a geologist and not an astronomer, so I really care actually what the ground is made of. And my interpretation says that this smoother stuff, that higher elevation stuff that was kind of cracked and funny looking, is actually made of water ice, just like people thought all along. But I've shown them how much is there and that it actually is still there. and I've measured the volume. And my best guess for how it got there was that there was atmospheric deposition, snow, fancy word for snow, during one of the recent high obliquity periods when that axial tilt was much greater. Okay, so in summary, this is the last slide. Kind of slacked on it, but we found a lot of water ice in Utopia, but it's not a lake. A lot of people, the takeaway, like if you learn anything from this talk, know that there's not a lake that I found on Mars. I've had a lot of I've had a lot of people misinterpret this, notably like the media, thinking that because I compared the volume to Lake Superior, the largest of the Great Lakes, because I compared the volume to a lake, that it is a lake, but it's not a lake. It's more like fluffy, snowy stuff with some dirt mixed in. And that's all I got.
Thank you, Martian Ice Queen. We got some time for some questions. Who's over there on the side?
Oh, that's a really good question. That's an extremely good question. Are you a geologist?
Can you repeat the question?
Yeah, I'm going to do it. So the question was whether or not there's any analogous deposits on Earth. And that's a really, really good question. A lot of planetary scientists, they come from like a physics or astronomy background, and they start pointing at stuff on Mars, and they come up with these theories that have no basis in terrestrial geology / reality. So looking at this, I mean, there's some analogous features. There's some stuff when we look at this, we're like, oh, that looks like permafrost environments. But normally on Earth, when we have these sorts of features form, there's a lot of melt involved. There's a lot of liquid water, but we're not seeing any evidence of that. So there's some evidence of analogous features there, but I would disagree that it's like what we conventionally think of as an Arctic permafrost environment. A better guess for what I think this might look like is something called nivio-aeolian, which is a fancy word for wind-blown snow. But we don't see these same sort of permafrost features, the cracks and the little depressions. So, I mean, yeah, kind of we see things like this on Earth, but not quite. And I think that's just because it's so Martian.
Right in front.
It seems to me that what you're describing is something more like a subsurface glacier. It's a little bit of rock.
Okay. So she asked me if this is at all like a subsurface glacier. And I'm extremely happy you started asking me about subsurface glaciers because that's what my master's thesis was on. And I just finished my master's today, actually. So these are not quite like glaciers. We see a ton of what you just described on Mars, these clean ice glaciers that are flowing with a little bit of rock and dirt on top. This is not that. This has dirt mixed in all throughout it, I think, based on the radar results. And it doesn't ever look like it's flowed. I mean, for a glacier to flow, you need to have enough ice mass that it starts deforming under its own weight. We're not seeing any evidence of that kind of deformation here.
On the side? Right there.
Do you see the other evidence of more layers? Because if Mars tilt flips from time to time, wouldn't this happen again and again, perhaps in the same location?
Yeah. So he asked if we see any layering in this or any more layers, any kind of evidence of this happening multiple times. Looking at this, we can't know if there was some sort of obliquity shift and redeposition. My intuition says that's not very likely, just because when we move from high to low obliquity, we lose a lot of that ice. It's kind of rare to see the preservation of ice like this, and it has to do with the amount of erosion that's happening in the area, the amount of lithic material, the amount of rocky material that's getting mixed in with it. So I don't think we can say definitively just from looking at this, but my intuition would say that it's more likely to have formed from one event. That's a really good question.
Up on the balcony?
Mars has clouds, got ice. Does it have a weather system?
So he asked, we see ice, we see clouds, does Mars have a weather system? And yeah, I would say that it does. I mean, we have local temperature changes, we have dust storms, we have clouds, we see fog, we see water ice fog in some places, notably in Valles Marineris, which is a really big canyon along the equator. So yeah, I'd definitely say that Mars does have a weather system. It's not as dramatic as what you might find on Earth, just because the dramatically lower pressure, it's got a 1% the atmospheric pressure of Earth. But yeah, I'd say Mars has weather.
In the back with the gray shirt?
Can water on Mars melt or does it always sublime?
Oh, that's a really good question. He asked me if water on Mars always melts or can it sublime. And I'd say almost like all of the time it sublimes, but we do see evidence of melt in the form of gullies. We see things that look like they were formed by liquid water flowing, notably along crater walls in the mid-latitudes, so that would be evidence of melt. We see things called recurring slope lineae in the more equatorial regions. These are controversial, but some people have said they might be related to liquid water flow. And we know from just what we've gathered from Martian climate that almost always we're going to get sublimation of water ice. Liquid water just generally isn't stable on the surface. But if it's salty enough, there might be conditions where transiently you could get liquid water on the surface very shortly. Yeah, maybe.
Right in front?
We have frozen sheets of ice on Mars. How far beneath the surface would they need to be, especially in the event that we land something there and we start drilling for the use of
Okay, so he asked if we do have frozen ice in the subsurface of Mars, how deep do they need to be? And this is particularly interesting because if we send humans to Mars and they have to drill, we need to know. With the data we currently have, I mean, we're concerned with this question about the very shallow water ice table. With the data we currently have, we can't see what's happening anywhere in the 1 to 10 meter range of the subsurface. The radar just isn't high enough resolution. So it's possible that this extends up to a few meters close to the surface, but from what we know now, it's anywhere between 1 and 10 meters below the surface of Mars. In the early 2020s, we're probably going to send another radar to Mars, which is going to be much higher resolution, and we'll be able to know exactly where this water ice table lies. I hope that more or less answered your question.
Right behind?
So you're saying that, what would be the depth of this ice? Is it sort of, is it homogeneous of ice and less? Sort of a composite glass, a wind-blown, layering composite?
Yeah, okay.
Homogeneous.
Okay, so she touched on the idea of how deep is this below the surface, and she also touched on the idea of heterogeneity in the content of ice. If I'm understanding correctly, you're wondering, is the distribution of water ice constant? Or because it's been windblown, are we going to expect different amounts of ice through different parts of the deposit? And I didn't get into this in my talk, but I'd love to show you at some other time if you're really interested. I did find that there was a correlation between the thickness of the deposit and the amount of water ice that was in it. And I could talk at length about my hypotheses for why this is the case, but yes, we do see some heterogeneity in the composition.
Bringing it home with the last question, my young friend over here.
You stated that there's a lot of ice here, but you also stated it's mixing with rocks and
Yep.
source material. Would this make it a better or worse spot for landing on Mars?
Oh, that's a very good question.
As opposed to something like Acidalia that you see on Mars.
So what exactly about Acidalia? Sorry, I'll repeat the question in a sec.
So as opposed to that there, what would make this a better or worse place?
Okay, so are you sure you mean Acidalia?
Yes, the deep questions.
And not,
The place you see in the Martian.
yeah, but do you mean, gosh, I don't want to sound, do you mean Acidalia or Arcadia?
Acidalia.
Okay, so I don't know a lot about what's happening in Acidalia, but because the composition of water ice in this, I mean, when I gave you the volumes, it was the volume of water ice. It wasn't the volume of the entire deposit. It was what we expect based on the proportion of this deposit that's water ice, how much water ice there would be there. So that's our Lake Superior. Acidalia, I mean, I thought that was more like volcanic than icy. So I guess the main difference there would be this has a lot of water ice resources, whereas Acidalia doesn't. In my opinion, though, as much as I love Utopia, I don't think it's a particularly interesting geologic target. It's got the water ice. It's got a lot happening there. But it tends to be a lot younger. We're not seeing a lot of the really ancient terrains through here. We're kind of in the northern plains. And I think the diversity in geologic targets, the amount of things we can learn about early Mars into the recent history, sort of that transition period and the holistic picture of Mars. If we're going to send humans to Mars, yes, this would sustain them. I think it's a great spot to land if you just want to survive on Mars, but if you want to do science, I think there's more diverse targets in this one.
Okay, great. Well, let's thank Martian Ice Queen again.